We covered the mechanics and basic use in the first module in reporting. This second, much longer module looks at the specific use cases and the larger business context of each report. We'll cover important concepts like the AI and scheduler data pools, the most common fields and columns, the types of statistical analysis performed by AI, and other important notions like trends. The first report is the Jobstream Summary, which uses AI data and Jobstream runs. The focus is the relative performance of operations in relation to their SLAs. To structure the report, we select one or more job streams or business areas and a reporting period. The report shows the successive runs of the job streams against the SLA. With this report, we're able to cast a wide net using large data samples and pinpoint job streams that are not performing as expected. We recommend using at least 30 days for the data to be useful. Finally, the report produces a table with numbers if your report is date-based. By grouping the report by job stream, we can graph the data in charts. Use the General tab to select the job streams and set the grouping and sorting. The default setting is Group by Dates, which shows job stream runs by day. Job streams are sorted alphabetically. You're able to select all job streams for a given business area, which is useful when you want to produce data for an entire team in the organization, say sales or finance. In the Runs tab, you select the status types, completed, in progress, and forecasted. We're looking to analyze completed executions, and we recommend a minimum of 30 days worth of data. You can drill further down by focusing on late executions to reveal job streams that fail to meet their SLAs. You have a date selector if you need to isolate a group of runs over a specific period of time. In order to show the evolution of the job stream over time, you must group the data by job stream. This enables the chart feature. The report is ready. It produces a summary and comes with a table of contents. The job streams are sorted alphabetically. This job stream is fairly stable, as shown by the graph. The points show start and end times, and the red line is the SLA. Columns include the number of jobs in the critical path, the successive runs and dates, run times, delays, and so forth. This job stream has a couple of outlier runs around 518 and 522. The Jobstream Detail report is a natural extension of the summary. It's another AI data and Jobstream report. It provides information for each specific Jobstream run and jobs in the critical path, and expands on the various types of delays which might cause an overrun. Delay information is incredibly useful for troubleshooting. When you're trying to improve a batch window through SLA contraction, you need to know what is holding back your executions. The job itself, the ops team, unsatisfied conditions, or something else. Only then can you fix it. The types of delays are as follows. The finish to start delay shows the length of time between when all job conditions have been met and the job actually starting. This indicates a system latency. The start to running delay shows a length of time that was inserted between the activated start of the job in the scheduler and the time of submission to the system, indicating possible latency in the scheduler or its hosting server caused by performance or processing capacity issues. Operational delays point to system submissions held back by failures resulting from errors, operator-initiated restarts, and so on. The job activates at 8 a.m., fails to execute, the operator is called to act, and restarts at 8:30. The operational delay is 30 minutes. Design delays point to system submissions held back by design. Say a job start set artificially to a hard time. A predecessor ends at 8 a.m., the job owner sets the critical path job to start at 9, you have a 1-hour design delay. Resource wait times point to executions held back while waiting for a virtual resource to free up and have enough capacity to execute the job. Unexpected delays are all delays that do not fall in the first 5 categories. The report is organized using the same data points as the summary, job streams and time. The report drills down into each run to reveal additional information, namely specific time spans associated with each type of delay. Whereas the summary produces a report with Jobstream level data, the detail report breaks down each Jobstream run with individual data points. The processing load report uses operational data to understand the busiest processing times during the day. It shows a time period on the horizontal axis with two charts. At the top, we see instances of delay with the two main types, finish to start in blue and start to running in orange. In the bar chart, for each time interval, you'll see starts, end, and in progress jobs. Using these two charts, you'll be able to correlate events and delays and identify possible system-based issues. For example, at 2:45, the volume of events is low but delays are high. That points to a potential problem on an agent, or perhaps on the automation engine itself. Note that another, far more detailed report showing the individual jobs running at any given intervals is available, but needs to be executed using the command line interface. The Termination Status report uses operational data from the schedulers. It shows totals for each status. The most immediate benefit comes from the consolidation of multiple scheduler data streams into a single place. The report is very flexible. There's a multitude of grouping and sorting options, filters, summary data, and more. The report produces data aggregates for past executions in the schedulers. You should specify a period and you can filter on time. Based on the selected schedulers, available statuses are listed. This can be quite useful if you want a report showing all schedulers and the failed status associated with each. It will show all failed executions for your entire operational landscape. You can narrow your query to individual jobs, parents, or other types of processes, such as events and atomic. If you uncheck the Job Runs box, you'll show only summary data in aggregated form, say 150 jobs with a failed status. Then you can sort the data by job name, parent, status, or something else. In the case of large volumes of data, you can have two levels of grouping. So you could group your totals first by scheduler and then by date. The report would contain several pages showing job runs that failed by date for a given scheduler. Since this data is sourced directly from the schedulers but is imported into AI before being converted to Jobstream data, you're able to apply filters from both the schedulers and AI. We recommend fine-tuning this report carefully into your specs, or it could be extensive and take a very long time to generate. The last two reports perform trend analysis and show the evolution of operations over time. Trend analysis casts very wide nets over large data samples to reveal needle-in-the-haystack opportunities for batch improvement with the highest upside. The first report looks at AI data, job streams, and critical path jobs. The second at scheduler data. As we explained, the Trending by Critical Path History report aims to improve batch windows through critical path contraction. It looks at Jobstream runs to reveal the lowest hanging fruits. Candidates are uncovered through the numbers found in the report's columns. First, the frequency of inclusion of a job in the critical path is important. We know that the biggest bang for our buck lies with jobs consistently present in the critical path. Second, runtimes play an important part. We'll see more substantial gains by reducing runtimes by hours rather than minutes. Third, we want to focus on trends. The problematic jobs are those whose runtimes are increasing over time, not decreasing. Taken as a whole, they have the potential to expand our batch window exponentially. We have the goodness of fit, which is a statistical standards. It's the product of all of our data points: frequency of inclusion, average duration, and trends. Higher goodness of fits means more qualified candidate jobs. Let's see how this translates in the AI graphs. First, let's consider critical path inclusion rates. Each dot is a run, blue when the job is excluded, red when included. We're looking for higher proportions of red dots in our graphs. Next is average duration. You'll find those numbers in the table and summary. Then we have trends. A job stream whose runtime increases over time means it's trending upward, steepening the curve. Bringing all those elements together produces the goodness of fits. Our last graph shows high fits, high frequency, high average duration, steep upward trends. This job is a good candidate for optimization, resulting in bringing your SLAs in earlier for this job stream. Depending on the type of data you wish to produce, you can change the sorting. Sorting by trend means the report will show the jobs whose runtimes are increasing the fastest first. You can change this, say, by sorting on the frequency of inclusion in the critical path, meaning the report will start with the jobs most often included in the critical path. The Trend Information tab is important. If you want to filter on trending data, you have to include it. Then you can apply useful filters. For example, you can reject all jobs whose runtimes are not trending up at a minimum rate. Or you can simply focus on the jobs with the highest goodness of fits. You can also include a graph, change the number of critical path jobs included in the graph for each job stream, and finally, you should exclude the parents, since the focus of our report is the unitary jobs, not compound objects like boxes and workflows. At the top, we have the summary data with the name of the job stream and the number of graphs. Columns show the percentage of inclusion, average duration, the trend, and goodness of fits. All numbers basically show that this job is not a suitable candidate for investigation, which is confirmed by the graph. This job is consistently in the critical path and has a fixed duration of 5 minutes. If you were able to reduce the duration of this job, you would likely have an impact on the SLA. However, since the job only runs for 5 minutes, the impacts may not be as significant in a long-running job stream. The last report, Trend by Job Run History, is similar, but uses scheduler data instead. It's one of the most useful reports in the solution because it allows us to uncover the best candidates for an optimization efforts. The report dialog provides a filter on jobs, which you can apply if you want to focus on certain definitions specifically. However, our recommendation is to cast the widest net, basically source all executions indiscriminately as the initial data pool, and then narrow it down to zero in on the candidates, say with a goodness of fit above 70%. AI will look at everything and isolate those job executions whose runtimes are trending up and are quite long relative to other jobs. The General tab has two main filters for the trending period and the job selection. Let's consider the period first. Out of the box, the default trending periods are 30 and 90 days. Although it's possible to apply an on-the-fly custom period for your report, we must advise against it. When you use predefined periods, say 30 or 90 days, AI Statistics Engine produces the data on a nightly basis when the workload is at its lightest, so as to not overwhelm it with custom requests, which take substantially longer and can have serious impacts on performance. You should always use set periods. Note that you have the option of creating your own training periods in the AI config tool. Then the statistics engine will generate for those as well. Let's look at job selection. We're trying to isolate those jobs that are good candidates for optimization. For this, we have the goodness of fit criteria. So we use the dot pattern since our atomic job names all have dots in them, and then apply the filter with a minimum of 70%. We're counting on the fact that the list of jobs with a very high goodness of fit is short. So we ask for details for the entire resulting job list and then apply the 70% goodness of fit criteria. We also exclude parents from the search results since this is not our focus. The list is short as we anticipated. There's a handful of jobs with a goodness of fit of over 70%. Notice that in certain cases, this number will be over 100%. This happens when the job definition itself, say the underlying batch process code, was altered by the job owner, and this happened during collection. Runtimes increase substantially as a result. You can ignore these jobs. You can also ignore jobs with low run numbers. This is an indication that they're not ordinary. They might be testing jobs or put in production very recently. The data sample is simply too small to be meaningful. This leaves our jobs.trend1 with 35 executions, a 56% trend, and a 93% goodness of fit. You should absolutely focus on fixing this job first.